Welcome back to the lectures on engineering electromagnetics. The discussion today will focus on electrostatics. So, earlier discussion, we were trying to understand the applications of electrostatics and we had a glimpse of Coulomb's law. We'll go into the details in this particular lecture. To understand it better, we first have to understand what is this point charge. As such, the basic electrical quantity is the charge Q. And then if we are trying to understand an isolated charge which is surrounded by an electric field that exerts a force on all other charges, we try to understand the expression for Coulomb's law better. So there's a charge Q2 at a distance r from a charge Q1 experiences a force given by Coulomb's law. This can be understood by our formula formulated by Coulomb, which Coulomb stated as that the force between the two very small objects separated in a vacuum or free space by a distance which is large compared to their size is proportional to the charge on each and inversely proportional to the square of the distance between them, where Q1 and Q2 are the positive or negative quantities of charges, and then R is the separation and K is the proportionality constant. The international system of units is considered in SI units. Q is measured in coulombs, and then R is in meters, and the force is in newtons. So our expression for force is F equal to K Q1 Q2 by R square, where K would be any constant. This constant of expression is given by 1 by 4 pi epsilon naught, where epsilon naught is again another new constant, which is called the permittivity of free space, and as magnitude is measured in farad per meter, given by epsilon naught equal to 8.854 into 10 power minus 12, which is equal to 1 by 36 pi into 10 power minus 9 farad per meter. So, if we are considering medium such as air or other gases, the permittivity is expressed as the product of permittivity of vacuum multiplied by dimensionless quantity called the relative permittivity epsilon r, which is given as the expression epsilon equal to epsilon r epsilon naught. For most practical applications, we consider epsilon naught to be 8.854 into 10 power minus 12 farad meter inverse. It's taken as the permittivity of both air and vacuum. As for air, epsilon r equal to 1. So this is an expression which we have to carefully evaluate based on the medium. But most cases, we try to confine the discussion to vacuum and we use epsilon equal to epsilon naught in the formula that we have defined for the Coulomb's law, and we try to evaluate the expression of the constant as 1 by 4 pi epsilon naught. So the vector form of Coulomb's law is the next important concept that we need to understand. In order to write the vector form of the Coulomb law, we need the additional fact furnished also by Colonel Coulomb. The force acts along the line joining the two charges and is repulsive. The charges are alike in sign or attractive if they are of opposite sign. If the vector R1 is located at Q1 and whereas R2 locates Q2. Let us say, as we see in this particular diagram, we can see here Q1 is at a distance of R1 from the origin and Q2 is at a distance of R2 from the origin. And the line joining Q1 and Q2 would be defined by the distance R12, which is given by R12 equal to R2 minus R1. And the expression for the formula of Coulomb's law is given as F2 equal to Q1 Q2 by 4 pi epsilon naught R12 square A12, where A12 is a unit vector in the direction R12 and is given by R12 by mod of R12, or R12 by R12 equal to R2 minus R1 by mod of R2 minus R1. Now, this is the vector form of Coulomb's law. And what is more important and fundamental here is Coulomb's law is linear, which defines that there is a mutual force. The force expressed by Coulomb's law is a mutual force for each of the two charges experience a force of the same magnitude, although of opposite direction. You might equally well write Coulomb's law that if we multiply Q1 by a factor n, then Q2, the force on Q2 is also multiplied by the same factor n. This is very important to realize that Coulomb's law is linear, because when we have n number of charges, the definition based on superposition will allow us to calculate the force due to different charges that are present in the field. It is also true that the force on a charge in the presence of several other charges is the sum of the forces on the charge rising from each other or the charge acting alone, as I mentioned. So F1 equal to minus F2 equal to Q1 Q2 by 4 pi epsilon naught R1 R12 square A21 equal to minus of Q1 Q2 by 4 pi epsilon naught R12 square A12. The electric field definition for a point charge is the next important concept that we try to understand after we have understood the force due to charges. So consider a single point charge fixed in a particular position, say Q1. And then if we move a second charge, let's say slowly around this particular charge, and we call this second charge as the test charge, Qt. Then if we are trying to evaluate an expression, the force as per our Coulomb's law is given as Ft equal to Q1 Qt by 4 pi epsilon naught R1 T square A1 T. Now if we are trying to write the force as a force per unit charge, and we try to define the electric field intensity E1 arising from Q1, where E1 is interpreted as a vector force arising from charge Q1 that acts on a unit positive charge, basically, or the positive unit positive test charge, taking Q2 value to be 1, and then E1 equal to Ft by Qt will give you Q1 by 4 pi epsilon naught R1 T square A12. Or generalizing this expression, the electric field is given by E equal to Q by 4 pi epsilon naught R square AR, where AR would be any unit vector along the line joining. So here fundamentally again we need to remember that like charges repel each other while unlike charges attract each other. So if we are having two positive charges, as you can see in figure A, they are repelling, and then if there are two negative charges, they are repelling, and then if we are having one positive and one negative charge, they are attracted. So the principle of superposition can be applied to determine the resultant force on a point charge Q due to other charges Q1, Q2 on to Qn, which gives us the generalized expression again based on what was our definition earlier, saying that the Coulomb's law is linear, which gives us F equal to Q by 4 pi epsilon naught sigma k equal to 1 to n qk r minus rk by r minus rk power 3. So electric field intensity can also be calculated on similar lines as E equal to Q by 4 pi epsilon naught r square r, or this can be given as Q into R minus R dash by 4 pi epsilon naught R minus R dash whole cube. Electric field at point R due to point charge located at R dash is evaluated from this expression. And similarly, we are having n charges, the electric field at a point by principle of superposition, which is applied to linear systems. As such is given by E equal to 1 by 4 pi epsilon naught sigma k equal to 1 to n q k R minus R k by R minus R k whole cube. So we are trying to evaluate this particular electric field for a particular problem. Let us say we try to evaluate the electric field at a point P 1, 1, 1, caused by four identical 3 nanocoulomb charges located at P1, 1, 1, 0, P2, minus 1, 1, 0, and P3, minus 1, minus 1, 0, and P4, 1, minus 1, 0. So how we evaluate this particular expression is what we'll see in this particular problem. So we are having in the xy plane four charges P1, P2, P3, and P4. And then if we are trying to evaluate the value of the electric field at a point P 1, 1, 1, how we evaluate the expression is what we see. So generalizing, we know that we can define the distance, vector distance R as AX plus AY plus AZ. And R1 would be something like AX plus AY. And we try to evaluate R minus R1, R minus R2, R minus R3, R minus R4, which would be like the distances between each of these points and the point where we are trying to evaluate the electric field. So the magnitude of R minus R1 would be evaluated to be 1. R minus R2 similarly can be evaluated. R minus R3 and R minus R4 would evaluate to square root of 5. And Q by 4 pi epsilon naught equal to 3 into 10 power minus 9 by 4 pi into 8.854 into 10 power minus 12. This gives us 26.96 voltmeter. So once we evaluate and substitute these values, we end up getting E equal to 26.96 AZ by 1, 1 by 1 square, which is like the unit vector, plus 2AX plus AY by root 5 into 1 by root 5 square plus 2AX plus 2AY plus AZ by 3 to 1 by 3 square plus 2AY plus AY AZ by root 5 into 1 by root 5 whole square, which gives us the electric field to be E equal to 6.82x plus 6.82ay plus 32.8 kJ volt per meter. These are typical problems that are normally encountered in electrostatics for calculation of electric field at a particular point due to the presence of different other charges. So then the discussion so far was confined to only point charge. But if we are having the charge distribution as shown in the figure to be a line charge or the surface charge or the volume charge, so the definitions that we have for the charge would slightly vary. So whatever Q value that we are having would be represented by line integral of rho L dl for a line charge, rho S ds for a surface charge, and volume integral of rho V dV for volume charge. And then based on these expressions, we would have to calculate the electric field due to continuous charge distribution as shown here, and then we would evaluate like what would be the electric field at a particular point, or if we are trying to take something like an infinite line charge, how the electric field is evaluated and how the infinite sheet of charge would evaluate a particular value. So this would be the topic of discussion in our next lecture. So these are some of the references. Most of the data is taken from Sadiko textbook, and then Cross and Fleisch by Electromagnitics with applications by McGraw-Hill, and then William Haight, Engineering Electromagnetics, McGraw-Hill publications. Thank you.